Educational Module. Machine Learning. Learning Unit. Advanced. Time Series, and Anomaly Detection. Time series are a form of data which is worth exploring since machine learning tools are often used for their analysis. Time series are used in the fields of speech recognition, statistics, signal processing, pattern recognition, econometrics, and in other fields too. A time series is a collection of observations, data points, made sequentially in time. Most commonly, a time series is a sequence taken at successive equally spaced points in time. Examples of time series could be considered the following. A song in digital form. The blood pressure. The stock of a company. The temperature throughout the day. Many more cases in real world. Time series face a set of unique problems/difficulties. The size of the data can be incredibly large, traditional similarity metrics are useless, the format of data can be different as well as other data-related problems. The tasks include forecasting, classification, clustering, rule discovery, anomaly detection, and they all require similarity matching between time series. Methods for time series analysis may be divided into two classes: frequency domain methods and time domain methods. The former include spectral analysis and wavelet analysis. The latter include autocorrelation and cross-correlation analysis. In data mining, anomaly detection, also known as outlier detection, is the identification of rare items, events, or observations which raise suspicions by differing significantly from the majority of the data. Usually such items represent bank frauds, credit card frauds, network defects, medical problems, errors in text, intrusion detection, or simple outliers in data. As a result, anomaly detection is also referred to as outlier detection. The importance of anomaly detection is high due to the fact that anomalies in data translate to significant, and often critical, actionable information in a wide variety of application domains. For example, anomalous MRI image may indicate presence of malignant tumors. Anomalies in credit card transaction data could indicate credit card or identity theft, and anomalous readings from a spacecraft sensor could signify a fault in some component of the spacecraft. Outliers can have a very big effect on classification. Here is what happens to a simple regressor when a single value, as a result of human error, is increased by 10 units. Anomaly detection techniques are split into three main categories. Unsupervised anomaly detection techniques detect anomalies in an unlabeled test data set under the assumption that the majority of the instances in the data set are normal, by looking for instances that seem to fit least to the remainder of the data set. Supervised anomaly detection techniques require a data set that has been labeled as normal and abnormal and involves training a classifier. This is similar to common machine learning approaches, with the key difference that the task has an unbalanced nature. Semi-supervised anomaly detection techniques construct a model representing normal behavior from a given normal training data set, and then test the likelihood of a test instance to be generated by the model. An example of using supervised classifiers for anomaly detection would be hyperplane-based classifiers such as SVMs and their large margin approach. The novelty detection problem can be viewed as finding a large margin hyperplane which separates fraction of the data points away from the origin. As far as terminology is concerned, in outlier detection the training data contains outliers which are defined as observations that are far from the others. Outlier detection estimators thus try to fit the regions where the training data is the most concentrated, ignoring the deviant observations. Outlier detection is also known as unsupervised anomaly detection. In novelty detection, the training data is not polluted by outliers and we are interested in detecting whether a new observation is an outlier. In this context, an outlier is also called a novelty. Novelty detection is also known as semi-supervised novelty detection. Real-world examples such as robust covariance, one-class SVM, isolation forest, and local outlier factor.